Today we're going to look at resonance. Here is a mechanical example of resonance where we have a mass, a bound mass, that will be driven by my hand up here. Think of this as an electron bound in an atom. And electromagnetic field's going to come in and get it to wiggle. Or it could be an entire atom, for example, like in carbon dioxide, where the oxygen is going to start to move. And the idea of resonance is that when I move, I have to be near the resonance frequency, which is the frequency that the bound mass would like to wiggle at. If I can hit that frequency, I'll go wild. Now notice that when I drive it, it always behaves in sync with me. So here it's going with me, but the response is not that great. If I go at a high frequency, the response is even less. But if I hit it just right, it'll go crazy, and that's resonance. So when you hit the resonance frequency of bound electrons with electromagnetic wave, you get the maximum effect. So we're looking at that today, and that is relevant to why the sky is blue. Dielectrics involves dispersion, all kinds of neat things come together in this class. And also, when we look at the idea of a bound electron, I'm going to do you a calculation that's basically off the top of my head, the back of the envelope calculations, which are very important in physics to make an estimate. And we'll do that to estimate the natural vibrational frequencies of electrons and whole atoms. And then we will look at the ultraviolet and infrared and make connections with environmental studies. In environmental science, two major issues are the ozone layer and ultraviolet light, and then infrared light and the greenhouse effect with carbon dioxide in the atmosphere. So we will be looking at those today also. So we have interdisciplinary connections today. And finally, when you think of driving an electron, when the electron starts to wiggle, it re-radiates, and that's important. So we have to understand that, and rather than go into advanced electromagnetic theory, there's a wonderful diagram and argument that can lead to the conclusion that the re-radiation will depend on the acceleration of the oscillation. And that will lead us to why the sky is blue. Chapter P, why is the sky blue? And that takes us to Rayleigh scattering, which we'll be covering today. Lord Rayleigh, John William Strutt, the third Baron of Rayleigh. He got the Nobel Prize in 1904. The Nobel Prize in Physics started being awarded in 1901. And we're going to look at his work involving scattering and the sky. Looking at these early Nobel Prize winners, Albert Michelson is listed here, as we saw earlier, measuring the speed of light. We have here Lorentz, 1902, of the Lorentz transformation fame, sharing here with Zeeman, the Zeeman effect in physics. We have J.J. Thomson, a student of Rayleigh's, and J.J. Thomson discovered the electron. You also have the Curies here, Pierre and Madame Curie, Marie Curie. And Marie Curie has the distinction of being the only scientist that has 2 Nobel Prizes in 2 distinct areas of science. She won the Nobel Prize in physics and the Nobel Prize in chemistry. Now we're going to trace back to Lord Rayleigh. You are here. If you're registered with me at UNC as a student, you're my student, but also if you're watching this from halfway across the world, you are getting knowledge transmitted through me. So this would be you too. You also are included here, whoever is listening. And let's trace back to Lord Rayleigh. How many generations? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 generations to Lord Rayleigh and his student, J.J. Thomson, the discoverer of the electron. First thing we're going to do today is to look at polarization. And this polarization is not the same as polarization of light. It's electric polarization. And with electric polarization in matter, we're looking at a situation where we have plus charge on a capacitor, upper plate, and here, bottom plate, the negative charge. 1, 2, 3, 4, 5, 6, 7, 8. They have the same amount of charge. And if we put in between a dielectric, something with electrical properties but not magnetic, is what we're interested in. Then here you'll get some negative at the top and some plus at the bottom. The charges can't move, but you can think of them as separating because of the electric field, and we call that a dipole when you have a plus and a minus. And the definition of a dipole with a plus Q and a minus Q with a certain distance d apart, where the vector goes from minus to plus, and I'm going to use a little p for this since it's a small dipole, is going to be equal to Q times the displacement vector. Now in this case, we're going to have 3 electric fields. One's going to be due to the free charges on the capacitor, and then here we have bound charges inside, because you can imagine all these, lining up so that in the middle they cancel plus and minus, but at the top there's a little negative part and a little positive part at the bottom. So you have what we're going to call the D field, which is due to the free charges. So if you take the capacitor out, that's what you have, and that would correspond with the E field. But we're going to save the E field for the total, due to the total charge, which has some reduction because of the polarization, that if you look at the minus and the plus here working against each other. So we're going to have these 3 vectors set up: polarization vector and E vector. And this polarization vector, I'm going to use capital P. It's the overall polarization that would be inside here if you drew these lines. And I draw the lines from negative to positive in reverse to what's usually done, because see, with the E and the D field, if you had a plus test charge, you would want to go to the bottom plate. Take that out for a second. But with the polarization, if you had a little test charge in here, so you'd want to go up to the negative, but we're going to pick down as a direction. So that being said, we're going to look at the Maxwell equation here, which we had earlier, and we're going to have the epsilon. This is the epsilon without the naught, and this is the Q free. We may have written that epsilon underneath that QF before. And we had these formulas. Let's write these down here. And we don't have to worry about the magnetic one, because we're not looking at magnetic materials. It says C is 1 over the square root, epsilon mu naught in vacuum, and the velocity of light in the medium would be epsilon without the naught, because we're in that new medium now, but the mu naught is still mu naught because it's not magnetic. And these two lead to the index of refraction, where if you look at this, this C has the epsilon naught on the bottom, and when you divide by the V, the epsilon will come up there. So these are basic equations that we had earlier. Now we're going to look at some definitions. So we're going to define the D vector by definition as epsilon times the E vector. If that's the case, we'll immediately have, for a Gauss's law, dot D dA, all right? And this is dot dA, and this is then Q free. Okay, then if we look at this formula up in here, which I'm going to write out as two terms, epsilon naught plus epsilon naught chi V. This is the electric susceptibility. This gives you the amount of polarization that happens. If there isn't any polarization, for example, then this is gone, then it's just like being in a vacuum. So this means that D, if I now use this equation, I'll have epsilon naught times E plus epsilon naught chi E times E. And this is defined by definition as the polarization, big P. And here, notice it points in the same direction. That's the convention. So once when we have this set up, we can now have a series of Gauss law type equations. For example, if we write out the Gauss type law here with the D, that has to equal the one with the E, with the epsilon naught in front. And this has to then be the one with the polarization vector. And since the free charge, you can think of that as have the net total charge minus the bound charge, because see, the bound charge is going to work against you. So this is the way you can set this up. So when you do this, you'll get the Gauss's equation for the first one, and the second one here, let's go ahead and write the second one out here. This would be equal to the Q total, which is what we want for E. E is always like the total. And then this last one over here, P dot dA, that'll be minus the QB. So let's try to understand the nature of this polarization vector by its dimensions. Well, the dimensions, since they're all on equal footing, are going to be the dimensions of all these have the same dimensions of electric field and the permittivity. Now, the electric field and the permittivity, we can get these quite easily because, see here, this combination here with if you put the area in, you're going to have, this is going to be charge. So if we were to look at, say, E naught, epsilon naught, and then the E dot to dA, this is a charge total. So that means these two are going to be equal to charge divided by area, right? Because take the area and bring it to the right-hand side underneath. So that's coulombs per square meter. Now, the cute little dipole has dimensions here. Let's go ahead and get that one down again. The cute little one, that's Q times D. That has dimensions here of coulombs times meter. So this is interesting. What this is teaching us is that to get the big P, the big polarization, we need to divide this one, the little one, by a volume. Because if you take, for example, C times M, that's the little one, and if you were to divide that by a volume, you would get then the big one. So that is exactly what we would want. In other words, the polarization, like the global polarization, is due to a density. This would be the number of babies you have per unit volume times the baby polarization. So that makes the connection, everything like fits together. So once we have this, we go back to our definition up here, which says that this says here that P, big P, is epsilon naught, and then you have this chi factor times the little e. This means that this constant, product here is going to be equal to P, big P divided by E. Okay, so we have the two equations here from before. Let's write these down again. And we can then write epsilon is epsilon naught plus epsilon naught. And we had earlier, by definition, that the polarization is equal to and we have the polarization proportional. So this makes sense that if you have a strong E field, bigger E field, you have a bigger polarization. Makes sense to do that, and how that we set that up. And if we do that, we get the epsilon naught chi E is now the magnitude. These are in the same direction. We have this. We have that. So that means we have the epsilon naught plus the P over the E. One last step here is we'll replace the big P with the NQ little p. Right. These are in the same direction also here. So that's saying the big P is NQ little p. So we have this cool expression. And then for the index of refraction, where we had the square root, if we square the index of refraction, we get then a nice expression. We're going to divide, put this in here and have 1 plus NQ little p epsilon naught E. That's a lot of work to get to a very fascinating formula where the index of refraction is now expressed in terms of these little dipoles. And that is just a fascinating formula, So I'm going to write this again. And we're going to box it off. I would like to call this section here that we just did P2, which has the title Index of Refraction and this polarization. All right. Okay, so we can call that section there. So the first section, and if you want, you could replace, the little p. It's related to the little p, so we can do that. So the first section was to get this polarization. Second was to then start with that and get the index of refraction into the game. So now we're going to look at something that's very fascinating, and it's a different kind of calculation that I'm going to show you. And we're going to talk about the bound charges. And here in chemistry, you have your nucleus and you have electrons, and outer electrons, little response to the electric field and shift a little bit, and that gets you a dipole effect. You can think of, in general, harmonic oscillator when you have a small displacement, and remember, if you have some kind of potential that's complicated, we don't really care how it looks as long as you have a little equilibrium there, you'll have oscillations. So we're going to study this in terms of, the oscillator, and if you get to the right frequency near these oscillations, you get a resonance. You can get a resonance effect. So let's try to find out the typical oscillations that would occur with electrons, and then we'll look at like carbon dioxide and look at a whole atom vibrating. Now this is a very, very powerful kind of a calculation, back of the envelope calculation, or one that you can be doing, say, on a bench with paper and say a pad and pencil and nothing else. So we're going to play the game of estimating what the frequency is for oscillating electrons in atoms. So what do I do? Well, for the harmonic oscillator, I remember that the energy, if you have your kinetic energy and your potential energy, that when the oscillator is going back and forth, when you get the maximum, you get no velocity. It turns around at the extreme, so it's Ka squared. This would be the energy of the system, of the oscillator. And I remember that we worked this out when we had the Newton's law, mass times acceleration is minus kx, and we had the second derivative, k over m, and then we used the sines and cosines, where you had, say, the sine of omega, say, naught t. Then when you took the two derivatives, you popped out two of these, so you had omega squared, that has to be equal to km, you get the negative sign, and then omega naught is the square root of k over m. So here, if you look at this, this k is m omega naught squared, and that means the energy here would be 1/2 m omega naught squared a squared. And I'm trying to figure out what this frequency is. So that omega naught squared would be 2 times the energy divided by m and the amplitude squared. So we're looking at here, for the frequency, I need a square root of 2 times the energy over m a squared. Now, what's the energy? All I remember from modern physics and chemistry is electron volts. Energies are in electron volts. And I remember in chemistry and in modern physics, I remember like distances are in angstroms. So I'm going to use these to do an estimate, like an order of magnitude estimate as to what is going on. So if we do this, we're going to have, for omega naught, looking for these characteristic frequencies of vibration, like I did earlier, the shoe on the end of a string. This is going to be 2 times 1 electron volt over the mass of the electron, whatever that is, and this is going to be here 1 angstrom. So 1 angstrom is going to be, well, this is squared, right? So if I take it out, if I take it outside, I'll have 1 over 10 to the minus 10th meters, because that's an angstrom. So just take this outside. So if you take the a squared outside, here is just the a coming out as 1 power. So at this point, I need to worry about the mass. Don't know what the mass is. I'm on a bench in a park. But I do remember, now here as a particle physicist, I remember, and in modern physics they may talk about this, E equals mc squared for the electron, because this is the mass of the electron. And this is, if you're a particle physicist, they'll tell you this so many times, like 0.511 million electron volts is the energy equivalent for the electron. And the proton is 938 MeV, and the neutron's a little bit heavier. All right, so you might not know that part because in modern physics they may not have stressed that. But anyway, I got this. So that means omega naught is going to be, over here I'm going to just divide, bring this on top like this. And that's going to be 1/meter, and then square root of 2, and this is going to be electron volt. And then here, what you're going to do, because you really want the mass, you need to divide by c squared. So this is a little tricky. So 0.511 MeV divided by c squared. That'll give me the mass of the electron. All right. Now let's go ahead and do the next step. 10 to the 10th, 1/meter, and this is 2 electron volts. C squared comes up top, that's 3 times 10 to the 8th meters per second. I'm going to square that in 0.511 MeV. Now let's check the units. Here you're going to get meters per second squared, and EVs will cancel. This is electron volts. This is a million. I'll have to put in 10 to the 6th. And then we're going to get the square root of meters per second, that whole thing squared. So that's going to get you meters per second. Cancel that, meters. You'll be left with 1/second. Because see, this 1/meter will be hitting meters per second. When you take the square root of the speed of light squared, it'll be meters per second. And the EVs cancel. So this is going to be 1/second. That's what frequency is. It'll be radians per second. So now that we got this far, we're going to then forget those units and just look at the numbers. And this is the square root of, well, let's do this. This 0.5 is a half. You should bring that up. It's going to be 4. 2 divided by 0.5 is 4. And this is going to then be 9 times 10 to the 16th, and then this is going to be 10 to the 6th. Here's where you have left off. So if we go with the omega naught, 10 to the 10th, take the square root of 4 is 2, square root of 9 is 3, and then this will be the square root 10 to the 16th over 10 to the 6th. That's going to be the square root of 10 to the 10th. So that'll be the 10 to the 5th. So this whole thing is going to be 6 times 10 to the 15th. This is 2 pi f naught, and 2 pi is about 6. So that means f naught is about 10 to the 15th hertz. Well, 10 to the 15th hertz, if I want to know what the wavelength of that would be, remember the wavelength times the frequency is the speed. So that's the speed of light divided by f naught. That's 3 times 10 to the 8th meters per second divided by 10 to the 15th per second. That's 3 times 10 to the minus 7th when we subtract meters, which is 300 times 10 to the minus 9th meters, which is 300 nanometers, and that is UV. So we have established that electrons have resonances in the UV. Now, what about an entire atom? For example, here B, oscillating atoms. If we look at the whole atom moving, actually the one that's going to be the nice one is going to be this one here, where they're going to move like this and then down like that. But to get an idea of what's going on here, I'm just going to take an oxygen atom. If I take an oxygen atom, has 16 nucleons, that would be protons and neutrons, and it has 8 protons. And I remember a chemistry teacher once saying that 1836 times the mass of the electron, and remember that as a date, is the mass of a proton. That is wild. Well, in particle physics, the proton, we know the proton's 938 MeV, energy equivalent, and this is 0.511 MeV. And if you were to divide the electron energy into that, you'll get the 1836. That's wild. I remember that as a date. I think my license plate even has that now. So I'm assuming here that the electrical forces, same kind of forces. So I'm just going to do here using the formula that since omega naught squared is 2e over ma squared, what I'm going to do here is that if I look at the ratio of the mass of the atom to the electron, I'll be able to scale down and get the new resonant frequency, because everything else I'm going to assume, same forces. In other words, omega naught goes as a square root, 1 over the square root of the mass. So I'm going to replace this. I'm going to look at this as a ratio. So if I have that, and then if I have, say, atom, that'll be proportional to the mass, square root of the mass of the atom. So the mass of the atom, it's a ratio we're going to look at. So if you have the omega for the atom divided for the omega of the electron, like this, then we're going to have, see, it's an inverse relationship. And you know that this is correct because if the mass of the atom gets very, very big, it's going to be sluggish, inertia, and the corresponding omega is going to go down. So if something's proportional to 1 over the square root of m, then when you look at the big one, atom, versus small one, you have to have small one here and big one down there, and square root. So we're just simply taking this and divide by that. The little m pops up. This is the electron one, pops upstairs. So let's look at this ratio. And for the mass of the atom, we'll use the 1836 times the mass of the electron to get 1 proton. And we want 16 nucleons, and protons and neutrons are about the same. So this is what we're looking at. This is going to cancel. And we're going to get the square root of 1 over, let's make this 1800, close enough, times 16. So the natural frequency of vibration for an atom is going to be equal to the natural frequency of vibration for the electron times this factor. So what do we have down here for 1800? Now remember, I'm on a park bench, my cell phone has died, and just have paper and pencil. And that's the game. I got to do this without looking anything up. So this is going to be here, this is 9 times 2 to get 18. Then there's the 100, and then there's the 16. So this is going to be then 1 over square root of 9 is 3. The square root of 2 and the square root of 100 is 10, and the square root of 16 is 4. This is going to take me to 3 times 4 is 12. That's 120 times square root of 2 is 1.4. All right. And this would say 1 times 120 plus 4/10 times 120, distributive axiom. And 4 times 12 is 48. So 0.4 of the 120 is 48. So this is going to be 1 over 168. And that's going to be, for the atom, we'll divide by 170. Now for the wavelength, remember the way the wavelength works. If you want the wavelength for the atom, the corresponding wavelength for the resonant frequency, this would be, you just have the inverse relation. That's 170 times the result for the electron. And the one for the electron, we figured out was 300 nanometers. And, 3 times 15 is 45. 3 times 16 is 48. And 3 times 17 is 51. So the characteristic wavelength for then the atom vibrating is 51. And this is amazing. This is, let's say, for the atom here. Atoms like to vibrate in the infrared. Isn't that marvelous? Look at that. This is IR, infrared. Since you're visible, it goes from 400 to 700. Amazing. If we move on to driven oscillations, this is all comes together where electric field's coming in that's wiggling, and it will make the electrons go wild at UV frequencies, and it'll make the atoms go wild at the other frequency. And that brings us to the ball on the end of the pendulum, where if you shake it back and forth like I did earlier, and do a little graph of frequency, applied frequency and response, you find that it does very little response when you go to low frequency. And at the high frequency, it was actually 0. It didn't do anything. And it did something crazy in the middle. So if you connect these together, you get the famous resonance graph, and it doesn't really matter if you want to put the wavelength here and the response, you just turn this, around the other way. You basically still get something like that, all right? With the electrons vibrating where this would be UV for the electrons and infrared for the atoms. So let's look at the ultraviolet in a little more detail. And you see the ultraviolet can be broken up with the visible here, an enlargement with the visible, and the ultraviolet to the left have these 3 categories: UVA, which is near the visible, UVB, moving farther to the left when you have the wavelength increasing to the right, UVC, and then extreme ultraviolet. Authors will differ a little bit about those cutoffs. Another way to look at it is if you have the near, this is another categorization of these colors. You might say these are colors. The near UV is 300 to 400 nanometers, meaning near the visible. And then mid, or the middle UV, would be another 100 interval, but now you go 200 to 300. And then the far UV would be 100 to 200. And then the extreme, like the extreme far away, would be 10 to 100 nanometers. Luckily, this radiation from the sun gets absorbed by the atmosphere. The extreme ones ionizes the atmosphere. We have the ionosphere in its atmospheric studies. This is a nice connection with the atmospheric studies and sciences. And then you get absorption by ozone, and other things contribute here. Ozone mainly absorbs 200 to 280 nanometers. And then some of the UVB here a little bit gets into the earth, and that causes suntan, and also vitamin D is related there. And then you have the UVA, which is very close to the visible, that though could maybe work on your skin over many years. So not sure. UV is not the best radiation there for you. So if we look at the ozone situation here, the ozone is in the stratosphere, and you can't really see here maybe that easily. This is the ozone layer. It's a very, very small region. And the ozone layer, it essentially, the way it works is in that area, you have, say, oxygen. And if you get UV light from the sun like that, you then get the oxygen split up into 2O. Now, oxygen is a double bond. And then here, this would be like free oxygen atoms. But then O2 will find one of those, and then you get O3, which is ozone. This is cool. You get now each oxygen has 2 bonds, and it's set up like that, kind of neat. Sherwood-Rowland showed that CFCs can destroy the ozone layer. Now, UV light can break apart the ozone, but that's UV is being absorbed in either case, and then it'll make some more. So as long as UV is being absorbed, you're in good shape. But what Rowland showed was that CFCs can destroy the ozone. Now, CFCs back in the 50s thought it was like as good as sliced bread. Like, it doesn't react. You could put poison, whipped cream, some kind of furniture finish, and shaving cream, for example, perfume. It then pushes, gives you that pressure to push out as a spray whatever you want to spray out. Say spray paint, or whipped cream, or perfume, or insect repellent. And that was 1950s. And then by the early 70s, made this discovery, and these CFCs don't react, and the CFC basically means carbon, fluorine, and chlorine. So CFC, like here's an example where you have a carbon likes 4 bonds, and stick a fluorine, say there, a fluorine there, and a chlorine there, and a chlorine there. And this is an example of freon. This is called freon 12, and then freon 11 would be, let's see, you have 3 CLs. DuPont came up with some of these names and using refrigerants and things, but then they started outlawing this for like shaving cream and things like that, like after this discovery, because the ozone is very, very protective. We want to keep that ozone. So here, what basically happens, see, you have, say, a chlorofluorocarbon. Say you have, let's say we have this one here, this freon one. Then when you have the UV coming in, the UV can break a bond, and you can get here a Cl by itself. Now, chlorine wants to react, man. It's not going to hang around alone very much. So when the chlorine then finds here ozone molecule, then it's going to grab one of those oxygens, ClO, and then you're not going to have the ozone. And the ozone is important because the UV UV wants to break up the ozone and then help form it and break it up and form it. So if you're taking the ozone away, that's not good. So that's the very, very serious environmental studies problem in the study. And Rowland got the Nobel Prize, and they shared it, and he came to UNCA. That's awesome. I believe Dr. Bert Holmes had him as a teacher, and it was interesting that when he was giving a talk, he mentioned his teachers and genealogy, and I believe he went back to Dalton, the atomic theory of matter, John Dalton, the chemist. Isn't that cool? And very graciously agreed to have a picture made with me with him. So we can add environmental studies to our list of interdisciplinary topics. The ozone, for example, very important with UV light, and the greenhouse effect, that's involving the carbon dioxide. And it's the carbon dioxide that wants to vibrate in this fashion, where it does this, and then it does this, that it'll absorb infrared light, and then it'll re-radiate it, but in all directions, preventing it from going straight through. And that is the greenhouse effect. Now, the greenhouse effect is really a little different than the greenhouse itself. This is at UNCA, the greenhouse. The greenhouse, the major thing that happens here is that hot air and cold air can't mix in the winter. But the greenhouse effect does, occur to some extent. And here's a better example. The greenhouse effect would be like in a car, where, for example, in comes the visible light through the window, the glass, and then the upholstery gets heated up, and the heat can't escape because glass won't let the heat out, and then it gets really hot. So this is a better example. And you should never leave animals in the car or a person in the car, a little kid or something, because in the summer the heat can build up so fast, and catastrophe. Someone can die. All right. So the idea here is that visible light comes in, and then the Earth gives off energy in the infrared that's trying to escape, and it can't get out of the carbon dioxide blanket. And since the Industrial Revolution, more carbon dioxide, environmental studies. And it's cool to spend some time, just a little bit, on the infrared, because they have similar kind of categories. You have the near infrared, which is near the visible. It goes from 700 to 3,000 nanometers in wavelength. And then the mid infrared, 3,000 to 6,000, far infrared, 6,000 to 15,000, and extreme infrared to 1,000,000. And then, boy, when you get this, this is, if you have nanometers, you have 10 to the minus 9, that's meters. And if you have 1,000,000, 10 to the 6, that's 10 to the minus 3 meters. That's a millimeter. So that's your microwave. That's when you start getting into the microwave. That's cool. So it's neat to see this, and mostly absorbed by the atmosphere. In fact, the atmosphere does a good job of absorbing pretty much everything we don't really want. Here, this is visible light comes through, and here you have. This graph here is actually opacity. So if you have this up here, that means you can't get through. So for visible, it's way down here, so that means you can get through. And then here, this peak here that blocks things out, this is like around your infrared, and your carbon dioxide would be in there. That's preventing it from coming through. That's the opacity, and then blocking all this. And look, you have here some radio waves can come through, because when this drops to 0, you're going to have some radio waves. These are shortwave radio waves. And it's kind of neat to see this, because this lets life exist. You have some ultraviolet, some have infrared, and then you have the visible, big window in the visible. And then here, this lets you talk to astronauts on the moon. It's nice to have that also. So here it's kind of cool. See, radio waves can be observed from outer space, radio astronomy. It works here for these waves. And here you got your visible. So these are like your two windows of the atmosphere. Now we go to the Lorentz model, which we need. And the Lorentz model, very, very powerful model of oscillator, the oscillator model. And here is Lorentz, Nobel Prize, which we talked about, known for the Lorentz transformation, known for the Lorentz force in E&M. And now we're going to look at the Lorentz oscillator model, which predates quantum mechanics, and see, you can think of the idea that, like a spring, and we talked about this before, that it doesn't matter what the forces are in chemistry or atomic physics or whatever, that if you have an equilibrium and do a little displacement, you have harmonic oscillator type behavior. And then with that harmonic oscillator behavior, we're going to have an incoming electromagnetic wave, something like this, I omega t, coming in, exponential notation to drive the charge. And then you have your equation, Lorentz force, like here. And this is very nice to see why you can get rid of the B field. Remember the connecting equation, E over B is equal to C. So that means that B is E over C. And if I put B in here, when I compare the strength of the electric field, you can see that you're going to have a velocity over C. And unless you're going near the speed of light or close to the speed of light, this is going to be thrown away. This is gone. So this is very, very small. So you don't have to worry about the magnetic field, just the electric field when those charges start to vibrate. So we already did this before, where we figured out that if you had your equation here, x double dot is minus, k over m x, remember we did that, and then this omega naught square root of k over m. And if we do it again, let's say where the force is now minus kx, but now we're going to add the driving force. Now we're going to drive it like that resonance idea, where you drive the sneaker on the end of the string to make it go wild. So if you just let it go, bowing back and forth, you get this. But what about if I drive it? I force it. It always goes at the rate that I am moving, but it may not move as much. And it may be a little bit out of phase. In fact, it's out of phase when you go at the high frequency. So here, this is mass times acceleration. And we could then look at this as a differential equation, mx double dot plus kx equals q. Here we're going to have to add the q because remember, for the force, you need to have the E, which is the E part here, times the Q. So you put the Q in there, and that's, say, E naught, E to the I omega T. And then if we put in for the Q electron, which is then going to be a negative, we'll have here x double dot, divide by the m, plus k over m equals, and there's the minus E, and divide by the m. So what we did here is we put for the Q minus E, and we divided by the M. So the M went away here, it's K over M there. And you have the denominator with M over on the far right. And then if you use the terminology, that this is omega naught, the natural frequency of, oscillation, you just square that to get the K over M. Then you have this cool formula, x double dot plus omega naught squared is minus E epsilon naught over m, e to the I omega t. And the solution is, as we expected, it's going to be, this is going to work. This is going to work. So if I put in here the same frequency, because I know it's going to force it like the shoe to do the same thing, then I'm going to try this out, put this in there. Then x dot is going to be I omega A e to the I omega t. In other words, it's I omega times itself, which we expect from sines and cosines. And then the second derivative here would pull another I omega down, and you get the same exponential back. So this is going to be minus omega squared x. All right. So let's look at what we have here. We have here minus omega squared from this part. And I'll just go ahead and put the x in, e I omega t with the a, and then plus omega naught squared, and then put the a, e to my omega t in there. And that's going to equal minus whatever's on the right-hand side. We put in there like that. And now you can see that we get some neat cancellations. This will go, and this will go. And then we'll have here A. We'll have omega naught squared minus omega squared. This one's go on there. That one's over there. And that's equal to same thing over on the right-hand side. We lost the exponentials. And that means the constant A would be minus electron charge, E naught, over M, omega naught squared minus omega squared. Now remember, our solution is x is equal to A, e to the I, omega t. So if you want the full solution, you're going to then put the A in front, like this. and then stick in your exponential. And this is the solution. And you can see when you get near the natural frequency of vibrations, things can go crazy. In fact, you'll get infinity. Now we're neglecting damping, we're neglecting friction. So if you go to Newton's law and you put in some friction, then that won't happen in real life. Okay, but now the fun begins. We know that the index of refraction is 1 plus NE, and this is the baby P, all right? The little polarization. We know this from before. And we know that the little polarization is Q times the D. But guess what? The Q is minus E, and the D is X. In other words, when you have the X moving and move the X a little d, you're going to get a dipole. If the electron moves down, this will be a minus and this will be a plus, the absence of the electron, see? And that's going to be your X. As your X is going back and forth, that's going to be the D. Isn't that nice? So if that's the case, then for the little polarization, we want minus EX, and we just now plug in this and get this very cool formula. The two negatives cancel. We get E squared epsilon naught over, just copy, M omega naught squared minus omega squared, and here's the E ti omega t. Now we're almost finished here. Remember, the big P is obtained by taking the density, the number density, and multiplying by the little p. So that means the polarization is, okay, so now we're going to put the NE there. We have the E squared. We'll have the E naught, E to the I omega t, and we'll have the M and the difference of the squares of the omegas. And now remember that the big P is epsilon naught chi E times the electric field. Remember that from before, the original setup? And that means that we can take this part and set that equal to the proportionality constant. But then we remember that epsilon is epsilon naught, 1 plus chi E. So these are familiar equations from before. So that means this part is going to be this, all right? This is really beautiful result. So when we do that, we'll have NE, E squared over M, and the difference. And then we remember that N squared is epsilon over epsilon naught. Remember, we had that formula as a square root that we squared. So that means we divide, we get 1 plus this. This is the beautiful formula that's going to teach us so much physics here when we apply it in a second. And we need to put an epsilon naught over there. The epsilon cancel there, but there's 1 going to be added to the right term here. This is the golden formula. Dispersion. This is dispersion formula. So we go to P6, dispersion, and this pulls together so much of our course. Dispersion revisited. Let's examine 3 cases, because this can apply to glass. I mean, this is dielectric, a glass. So we're going to go here first with low frequencies. That means omega is a lot less than omega naught. So we're far away from the resonance frequency. It'd be like me moving the sneaker very, very little, all right, low frequency. So then the limit as omega, that's the driving frequency, like my hand, and this is the frequency which the electrons would like to go at in the ultraviolet that we saw earlier. So if the driving frequency goes to 0, then you get 1 plus, in other words, the omega is going to go to 0. You then get n(e) squared over epsilon naught m omega naught squared, and that's a constant. Well, that's what we got. With the index of diffraction here for glass, these are different glasses. Look at them. At the low frequency means long wavelength. When the driven omega, the one coming in, when you're driving the system at a low frequency, when this is going to approach 0, that means the lambda is going to go large. So that means we're out here to the right. Look at these, they're all flat. Very nice. Then 2, suppose we have the driving frequency that's going to be near the resonant frequency. Whoa. Then that means this thing's going to shoot up like crazy, man, because if you're going to get near, you're now starting to, you start out at 0, but now you're getting closer and closer and closer, and you're still, less. This is going to shoot up, and look what happens here. These things start shooting up like crazy. They're going up, they're going nuts. When you get to the UV, see? When you get to the UV, they're going nuts. They're like shooting up like crazy. So that it helps us understand dispersion graphs so well. But then what about if you take another case where the frequency goes crazy and goes like, the driving frequency is like going to go to like super large, like if you're going to infinity. So now the frequency is a lot greater than the resonant frequency. Well, if this omega starts to get bigger and bigger, shoots off to infinity, this thing's gone. And you get n squared equals 1. What? N equals 1? That means the light will go straight through, like a vacuum. Well, guess what's on the other side of ultraviolet? X-ray. Pass right through. Now, not all X-rays, but you find with the hard X-rays, they'll go right through the glass. So this is so much physics we understand by this that comes from the polarization and the dielectric and the things we did earlier. So now this is the big payoff to understand the dispersion relationship and to understand here that the X-rays here, so very, very high frequencies. So we cover so much of the spectrum today. The infrared, actually infrared is here. This is infrared. See, this is the visible is over here. So here's the infrared. See, so that's really flat out there. And then we get to the visible, still pretty flat, but then starting to get near the ultraviolet to go crazy. And then the X-ray over there is going to come down, be 1. P7, why is the sky blue? Now let's write down an important equation we have derived. This one here, the harmonic oscillator, remember that we are driving a charge up and down, and this is the motion x, up and down. Now, this figure is very, very rich and will help us understand something very advanced in electromagnetic theory. And that is when there's an acceleration, you shake off electromagnetic waves. See, if a charge moves at a constant speed, that's not going to give an electromagnetic wave, and it can't, because like in relativity, if the charge is at rest and you move at constant speed by it, you're not going to see light all of a sudden. So you have to take that charge and wiggle it. So here we have a wiggling. Charge is wiggling back and forth. The center is at this red point, and the black is the top and the blue is the bottom, is wiggling up and down. It goes the fastest at the middle, and we'll call that V naught. We'll need that in a second. And we're going back and forth. Now, at t equals 0, we're at this red place, moving upward, and we start to decelerate, and we'll come to momentarily at rest here. So let's look at some of the times here. T equals 0, we're at the red circle. T equals tau, the deceleration ends, we're at the black. Time t, big T, that's in the future, where the light information, electric field, is traveling outward. And here, at this point, since this is t is equal to 0, at t is equal to big T, then the information of that position, because if you move, you don't have instantaneous results. It takes time for the information to get out there, the electromagnetic information. And here, if you then multiply the speed of light times big T and wait later to some future, then you'll have this sphere, the red sphere. When this particle gets to the top and momentarily is at rest, it would not have enough time to get to that bigger sphere yet, because it would have started later. In other words, that's a tau offset, little tau there is offset. So therefore, this shell is away from the outer shell by the speed of light time to time differential, tau. Now, here's the trick. You imagine that this particle kept moving straight up for that long time, big T. And we neglect this size here. It's very, very small. And we can take the two spheres to be concentric, since this is a very, very small oscillation. So now we use distance as velocity times time. That's the D. But what I'm interested in is this perpendicular component of the electric field that's going to be set up. I'm not going to be looking at ER as being transmitted as a wave, because you can't go radially in that direction, but this is sideways, that could radiate upward. So I'm interested in this component, but I can do it by this trick, which is the velocity times the time here, times the sine of theta is that distance. This distance is the velocity times the time t, and this is the sine of theta, this one here. And if I divide by this one, I get the nice ratio, and that's the one we talked about earlier, is c, speed of light times tau. So that brings us to E theta over ER is your V naught big T sine of theta, and divide by c times tau. Now I'll write this out with the ER here, and this is the Q over 4 pi epsilon naught R squared. This is your Coulomb's law, the electric field. And then remember, back to here, since this tau is much smaller than this future time, R, the radius, this radius basically for this part of the calculation, R is C times T. So we have C times big T is R. All right, now with these formulas, we're ready to go. The big T is R over C. That is going to go in here. So now let's write all this out. V naught. I'm gonna put the tau under the V naught. And then here, this R over C is gonna give me, we'll put R over C squared. And then we'll have the Q 4 pi epsilon naught R squared. The Q is gonna be minus E. So we come down here, and this is the key. This is the velocity you were going at the middle, and then here you are at rest. We're talking acceleration. So if we take the absolute magnitudes of everything and say we have a V naught, and we had, like, there was 0 to V naught or V naught to 0, the absolute magnitude of the acceleration is divided by the tau. So this is the acceleration, and that's the key that gets us the radiation. 1r cancels, you have a minus sign, E 4 pi epsilon naught c squared r sine of theta is also to be included, which we had dropped. And this is a theta. That's the key equation. That's an advanced equation. But the key idea is the acceleration. And that's all I care about, because the acceleration is going to get me the radiation. So what I need to do is find the acceleration, which is x double dot, and that'll pull down I omega twice. So that's going to get me I omega twice, that'll be an omega squared. And I only care about the frequency dependence. I don't care about anything else. So that's what I'm going to get. And since that is going to be an amplitude of the acceleration, to get the intensity, I'm going to need to square it. Have omega to the 4th over the denominator squared. And then if I look at omegas that are a lot less than the resonance, since the resonance is going to be more like in the ultraviolet, I'm interested in wavelengths that are, away, the visible. Then the intensity is going to go as, with omega being real small compared to omega naught, I can kick it there. And this is proportional to 1 over the wavelength to the 4th power. That's the famous result. So when the wavelengths are short, like the violet, then to the 4th power, 1 over that, it's going to be large. In other words, the violet has a higher frequency than the red. And there you have the effect. And here's the blue sky over UNCA. Why the sky is blue. And when you have the sunset and there's more atmosphere to come through, then more of the blue short wavelengths get scattered. But then, some of the greens are getting affected more and more. And if you take white and take away the blue end and a little bit of the green, you get reddish orange. You get the red sunset. So that explains a lot today.